Welcome to Back 2 of the Basic Statistics Review. We have discussed sampling, data collection method, and levels of measurement. Now we need to talk about how to deal with the data you have collected. Descriptive statistics are used simply to describe the samples that you have concern with. Measurement of central tendencies are most basic and often most informative description of a population characteristics. They describe the average member of population of interest. There are three measures of central tendencies. Mean, which is the sum of a variable's value divided by the total number of values. Median, the middle value of a variable. And mode, the value that occurs the most often. For example, the income of 5 random selected people in the United States are 10,000, 10,000, 45,000, 60,000, and 1 million. So the mean income is equal to 10,000 plus 10,000 plus 45,000 plus 60,000 plus 1 million, and divide by 5, which is 225,000. The median income, which is 45,000, and the model income is the 10,000. The mean is most commonly used to measure the central tendency, and median are generally used when few values are extremely different from the rest of value. It is called a skew distribution. For example, the median income is often the best measure of the average income because while the most individuals earn between 0 and 200,000, a handful of individuals earns millions. Measures of dispersion provides information about the spread of variable values. Range is simple the difference between the smallest and largest value in the data. And coefficient of variation, this is useful to see how much variation occurs in your data set. The higher it is, the more data points you need to collect to be confident that the sample is representative of the population. It can also be used to compare variation between the data sets. Variance is most commonly used to measure dispersion. It is calculated by taking the average of score difference between each value and mean. This is the most difficult value to use and needs only to be considered when using t-test or ANOVA. Standard deviation is another common use of statistics, and that is the square root of the variance. Useful to assess how variable a sample is, but the coefficient of variation is easier to use. The standard error of the mean is a method used to evaluate the standard deviation of a sample distribution. It is also called the standard deviation of mean and is abbreviated as SEM. For instance, usually the population mean estimate value is the sample mean in sample space. If we pick another sample from the same population, it may give you a different value. Hence, a population of sampled mean will occur, having its different variance and mean. The sample error of mean could be said as the standard deviation of such a sample mean, compressing all the possible samples drawn from the same given population. SEM represents an estimate of standard deviation which has been calculated from the sample. The The 68, 95, and 99 rule is based on the mean and standard deviation. It says 68% of the population is within 1 standard deviation of the mean, and 95% of the population is within 2 standard deviations of the mean, and 99.7% of the population is within 3 standard deviations of the mean. Statistical tests are used in hypothesis testing. They can be used to determine whether a predictor variable has a statistically significant relationship with an outcome variable. It can also be used to estimate the difference between the 2 or more groups. Statistical tests assume all known hypotheses of no relationship or no differences between groups. Then they determine whether the observed data fall outside of the range of the value predicted by the null hypothesis. Statistical tests work by calculating a test statistic, a number that describes how much the relationship between variables in your test differ from the null hypothesis of no relationship. For example, the test statistic of t-test is t-value. The test statistic of NOVA and chi-square test are f-value and x-square value respectively. It then calculates the p-value. The p-value estimates how likely it is that you will see the difference described by the test statistics if the null hypothesis of no relationship there is true. P-value indicates how likely it is that a result occurs by the chance alone. P is equal to the level of significance, which is typically 0.05. If the value of statistic test is more extreme than the statistics calculated from the null hypothesis, then you can infer a statistically significant relationship between the predictor and outcome variables. If the value of test statistic is less extreme than the one calculated from the null hypothesis, then it can infer no statistically significant relationship between the predictor and the outcome variables. In practice, you will almost always calculate your test statistics using statistical programs such as SPSS, R, Excel, and etc., which will also calculate the p-value of the test statistics. Confidence intervals are calculated from the same equation that generate p-value, so not surprisingly, there are a relationship between the two. The confidence intervals for measures of association are often used to address the question of statistical significance, even if p-value is not calculated. An easy way to remember the relationship between a 95% confidence interval and a p-value of 0.05 is to think of the confidence interval as arms that embrace the value that are consistent with the data. If the null hypothesis is embraced, then it is certainly not rejected. For example, the p-value must be greater than 0.05 if the null value is within the interval. However, if the 95% confidence interval excludes the null value, then the null hypothesis has been rejected and the p-value must be less than 0.05. If you took any statistical class before, you probably have already noticed that one way of stating the null hypothesis is to state that a risk ratio of odds ratio is 1.0. So you also notice that the point estimate is the most likely value based on the observed data, and the 95% of confidence interval quantifies the random error associated with our estimate, and can also be interpreted as the range within which the true value is likely to lay with the 95% of confidence. This means that the values outside of 95% confidence interval are unlikely to be the true value. Therefore, if the null value is not contained with the 95% interval, then the probability that the null is the true value is less than 5%. Conversely, if the null is contained within the 95% confidence interval, then the null is one of the values that is consistent with the observed data, so the null hypothesis cannot be rejected. In statistics, a type 1 error is a false positive conclusion, while a type 2 error is a false negative conclusion. Make a statistic decision is always involving with uncertainties. So the risks of making these errors are unavoidable in hypothesis testing. The probability of making type 1 error is the significant level, or alpha, while the probability of making type 2 error is the beta. These risks can be minimized through carefully planning in your study design. Using hypothesis testing, you can make decisions about whether your data supports or refute your research prediction with null and alternative hypothesis. Hypothesis testing starts with the assumption of no difference between the group or no relationship between the variables in the population. This is the null hypothesis. It is always paired with alternative hypothesis, which is your research prediction of an actual difference between groups or a true relationship between variables. Then you decide whether the new hypothesis can be rejected based on your data and the result of a statistical test. Since these decisions are based on probability, it is always a risk of making wrong conclusion. If your results show statistical significance, that means they are very unlikely to occur if the null hypothesis is true. In this case, you will reject your null hypothesis, but sometimes this may actually be a type 1 error. If your findings do not show statistical significance, they have a high chance of occurring if null hypothesis is true. Therefore, you fail to reject your null hypothesis, but sometimes this may be a type 2 error. Type 1 error is also known as a false positive error, the error of rejecting a null hypothesis when it is actually true. In other words, this is the error of accepting the alternative hypothesis when the result can be attributed to chance. Plainly speaking, it occurs when we are observing a difference between in truth there is none. For example, you conclude that the drug intervention improved symptoms when it actually didn't. Type 1 error is also known as a false positive error, the error of rejecting a null hypothesis when it is actually true. In other words, this is the error of accepting the alternative hypothesis when the result can be attributed to chance. This improvement could have arisen from other random factors or measurement error. A type 1 error means rejecting the null hypothesis when it's actually true. It means concluding that the results are statistically significant when in reality they come about purely by chance or because of unrelated factors. The risk of committing these errors is significant level you choose. That's a value that you set at the beginning of your study to assess the statistical probability of obtaining your results. The significant level is usually set to 0.05 or 5%. This means that your result only have a 5% of chance of occurring or less if the null hypothesis is actually true. If the p-value of your test is lower than the significant level, it means the results are statistically significant and consistent with the alternative hypothesis. If your p-value is higher than the significant level, then your results are considered statistically non-significant. To reduce the type 1 error probability, you can simply set a lower significant level. Type 2 error is also known as the false negative error. So the error of not rejecting a null hypothesis when an alternative hypothesis is true state of nature. In other words, this is the error that failing to accept the alternative hypothesis when you don't have adequate power. Plainly speaking, it occurs when we are failing to observe difference when in truth there is one. For example, you conclude that the drug intervention did not improve the symptom when it actually did. Your study may have missed the key indicator of improvements or attributed any improvements to other factors instead. A type 2 error means not rejecting the new hypothesis was actually false. This is not quite the same as accepting the null hypothesis because hypothesis testing can only tell you whether to reject the null hypothesis. Instead, the type 2 error means failing to conclude there is an effect when there is actually one. In reality, your study may not have had enough statistical power to detect the effect of certain size. Power is the extent to which a test can correctly detect a real effect when there is one. The power level of 80% or higher is usually considered acceptable. The risk of type 2 error is reversely related to the statistical power of a study. The higher the statistical power, the lower the probability of making a type 2 error. Statistical power is determined by the following factors. 1. The size of effect, which is the larger effects are more easily detected. 2. The measurement error. Systematic and random error in recorded data reduce the power. 3rd, the sample size. Larger sample reduce the sampling error and increase the power. The last, significant level, increase the significant level, increase the power. So to reduce the risk of type 2 error, you can increase the sample size or the significant level. The type 1 and type 2 error rates influence each other. That is because the significant level affects statistical power, which is inversely related to type 2 error rate. This means there is an important trade-off between type 1 and type 2 error. Setting a lower significant level decreases type 1 error risk, but increases type 2 error risk. Increasing the power of a test decreasing type 2 error risk, but increase a type 1 error risk. For a statistician, a type 1 error is usually worse. In practical terms, however, either type of error could have worse depending on the research context. A type 1 error means mistakenly going against the main statistical assumption of a new hypothesis. This may lead to new policy, practice, or treatments that are inadequate or wasted resources. In contrast, type 2 error means failing to reject a new hypothesis. It may only result in missed opportunity to innovate, but this can also have important practical consequences. You can perform statistical tests on data that have been collected in a statistical valid manner, either through an experiment or through observations made using probability sampling method. For statistical tests to be valid, your sample size needs to be large enough to approximate the true distribution of the population being studied. To determine which statistical test to use, you need to know whether your data meets certain criteria or assumption and the type of variable that you are dealing with. Statistical tests make some common assumption about the data that they're testing. First assumption, independent of observations. The observation or the variable you included in your test are not related. Second is the homogeneity of variance. The variance within each group being compared is similar among all groups. If one group has much more variation than the other, it will limit the test effectiveness. Third, normality of the data. The data follows a normal distribution. This assumption applies only to quantitative data. If your data do not meet the assumption of normality or homogeneity of variance, you may be able to perform non-parametric statistical tests, which allow you to make comparison without assumption about the data distribution. If your data do not meet the assumption of independence of observations, you may be able to use a test that accounts for structures in your data. This is all I want to discuss in the second part of the basic statistical review. In the third part, I will spend the time to talk about the statistical tests and how to use them.